Hey Chem Kids, Campbell here. In today's video, we're going to talk about the gas laws. You're going to need to be able to name some of the gas laws and use them to solve problems. Now, you've actually experienced some of the gas laws already. Remember on the second day of class when we played with the computers and the simulation? Well, we were actually studying the gas laws. We just didn't have names for them yet. So let's talk about what are they. Well, there are four real important names in the gas laws. The first guy is Robert Boyle. He was British. He studied the effect of pressure and volume. There was Jacques Charles. He was French, and he studied the effect of volume and temperature. Now, he actually never published his work, so he's kind of lucky. They call it Charles' Law. He's actually, the reason why they do call it Charles' Law, even though he didn't publish his work, is because of this guy. Gay-Lussac. Gay-Lussac actually studied pressure and temperature. He was also French, and he confirmed Charles' work. So did actually John Dalton. And so they decided, because Charles is the initial guy, that they'd credit him with it. And then, of course, our friend Avogadro. Remember Avogadro's number, 6.02 times 10 to the 23rd? He was all about amount, right? That's the amount of particles in a mole. He actually studied the effect of amount on volume. That's a lovely picture, isn't it? Now, the first three laws can actually be combined into one gas law. That's called the combined gas law. So we're going to talk about the first three laws today. We'll save Avogadro's for in class another day, and about the combined gas law. So first, let's talk about Boyle. Boyle, like I said, studied pressure and volume, and what he found is that when volume went down, pressure went up, right? I could feel that. You can feel it. You squeeze a bottle of air and you shrink its volume, or like a balloon, right? You can feel the pressure going up, right? Now we've got more collisions going on. Now, when we use Boyles' Law, so Boyles' Law says the pressure times the volume at one condition equals the pressure times the volume at some other condition. This is only the case when temperature and amount are constant. That's when we use Boyles' Law. So temperature and amount constants. And we can multiply the pressure and volume at one condition, and it'll be the pressure times the volume at any other condition. So write down that. Charles' Law, right, he studied volume and temperature, and what he found is that as temperature goes up, volume goes up. So think about like a balloon, right? It gets hot, the balloon gets bigger. Or remember our scenario number 1 from the first video? I put those balloons outside where it was really cold and they shrunk. So that was Charles. So what Charles found is that if you divide the volume by the absolute temperature at one condition, that'll equal the volume divided by the absolute temperature in another condition, provided that the pressure and the amount are constant. Now I say absolute temperature, that means Kelvin. You have to work in Kelvin. You're going to see problems where I give you two temperatures and they're in Celsius, and you're just going to want to plug them in, but don't. You've got to add 273 to a Celsius temperature before you calculate anything in this unit. Don't forget. Our last law, Gay-Lussac's law, he studied the effect of pressure and temperature, and he found also that this is a direct relationship, that as pressure goes up, temperature goes up, or vice versa, temperature goes up, pressure goes up, right? Usually we change the temperature. So he found that pressure divided by temperature at one condition is equal to pressure divided by temperature at another condition. And again, that's absolute temperature, temperature in Kelvin. And again, our constants would now be volume and amount. Well, we can take all three of these laws and put them together into one law, and that's called the combined gas law. So it combines all three of these laws into one equation. The combined gas law, you notice that it's pressure times volume divided by temperature at one condition is equal to pressure times volume divided by temperature at another condition. Notice Avogadro is not a part of this. The amount is not a part of it. We're going to talk about his law in another video. Now again, temperature has to be in Kelvin. But when we use, if you will get actually the combined gas law on your test, and in order to solve a Boyles law problem, all you got to do is cover up the constant in the equation. So for example, say temperature is constant. P1 times V1 is equal to P2 times V2. Whose law is that? Oh yeah, that's Boyles Law. What if pressure is constant? Then I have V1 over T1 is equal to V2 over T2. Whose law is that? If you said Charles, you are correct. What if volume's constant? Then I have P1 over T1 equals P2 over T2. Whose law is that? Gay-Lussac! Woo! So the combined gas law is a way for us to solve all the problems. We just ignore the variable that is constant. So let's take a look at an example of Boyles Law. I have a gas that has a volume of 3 liters when I'm at 2 atmospheres, but I'm going to ratchet up that pressure, and I want to know what is the new volume going to be at 4 atmospheres. Well, I don't talk about temperature at all in this, so temperature must be constant. So let's write down our variables. The thing that students mess up the most is making sure that they put the right conditions together. So what is our P1 and our V1? Well, look for the at. This links our volume and our temperature together. So this here is one condition. So our P1 is 2 atmospheres and our V1 is 3 atmospheres, which means that our other pressure is our second pressure. So our P2 is 4 atmospheres, and I want to know what the volume is. Well, this is Boyles Law. P1 times V1 is equal to P2 times V2. So plug that in to our Boyles Law equation, or just cut the temperature out of that combined gas law, and see if you can get the correct answer. Well, that's annoying. If you got 1.5 liters, you are correct. So take 2 times 3 and then divide by 4. Cool. That's Boyles Law. How about we try a Charles Law question? I have a gas that has a volume of 3 liters at 127 degrees Celsius, and I want to know what is its new volume if I ratchet up the temperature to 227 degrees Celsius. Now, what did I say about temperature? I told you I'm going to give you the temperatures in Celsius, but you cannot work with them in Celsius. You have to add 273 and make them Kelvin. In fact, if you don't believe me, you can try Charles' Law, leaving them in Celsius, and I bet you're not going to get the right answer. All right, so let's list our variables out. There's our at up here. So our conditions for T1 and V1 are 3 liters at 127 degrees Celsius. So we add 273, that's 400 Kelvin for our T1. And then our T2, again, add 273, that's 500 Kelvin. So out of the combined gas law comes pressure. If I don't mention pressure, that means it must be constant. Same with amount. And I'm going to take volume 1 and divide by temperature 1. And then I'm going to cross multiply, so I'm going to multiply by T2. Plug your numbers in and see if you can do the right algebra. If you got 3.8 liters, you did it correct. So remember, divide our temperature, our volume by our temperature, and then cross multiply. This baby comes up here and multiply by 500K. Now, check. Do it in Celsius. See if you get 3.8 liters. You will not. Must work in Kelvin. All right, we're going to try 2 combined gas law problems. So our initial conditions in this is we have a volume of 0.18 liters, a pressure of 0.8 atmospheres, and a temperature of 29 degrees Celsius. I want to know what the new temperature is at 90 milliliters and a pressure of 3.2 atmospheres. So we're going to set up our data table, but I want you to pay attention to the units. The units have to be the same on both sides. So where's my problem? Well, one problem is the fact that I'm in Celsius and I need to be in Kelvin, but take a look at your units for volume. I have 0.18 liters, cool, right units, but my second conditions, I'm in milliliters, so I need to convert my milliliters to liters. So let's divide by 1,000, or move that decimal place over 1, 2, 3. All right, so here's what our data table should look like. Here's pressure 1, our 0.8 atmospheres, our volume 1 of 0.18 liters, and again, add 273, so our temperature is in Kelvin. Our second conditions, we're in atmospheres still, so that's cool, but we have to convert that milliliters to liters, must work in the same units on both sides of the equation. And we're going to solve for temperature. So plug your variables into this combined gas law and see if you can do the right algebra. Pause the video, do some math, and let's see. Now, when you solve this, you're going to get a temperature in Kelvin. So if you got 604 Kelvin, you did good math. But I didn't ask for the temperature in Kelvin. I asked for the temperature in Celsius. So what do we got to do? We got to subtract 273. And that'll give us 331 degrees Celsius. That's the answer. Again, you can't work in Celsius. You have to work in Kelvin. Make sure you work in Kelvin or you won't get the right answer. All right, same initial conditions, but our second conditions, our pressure, volume, and temperature 2, are now going to be changed to STP. What does that mean, STP? So hopefully you have in your notes that standard temperature is 0 Celsius, which is what in Kelvin? 273, and standard pressure is 1 atmosphere. So our initial conditions are still the same as they were in the last problem, 0.8 atmospheres, 0.18 liters, and 29 plus 273 to get to Kelvin. But now our new conditions are a pressure of 1 atmosphere, so pressure went up, but temperature went down, right? Because standard temperature is 273 Kelvin. So I wonder what happened to volume. Did it go up or down? I don't know. Well, do some math. Come to class. We'll see if you got that math right. All right. Remember to fill in the turn-in sheet and turn it in when you come to class tomorrow. That's what we're going to talk about, and we're going to see if you got this answer right. See you in class.